Okay, so this is the lecture on arc length. Now it's the portion of rectangular arc length. So tomorrow we'll talk about parametric arc length. It's similar, but just a little bit different. So we're working with rectangular arc length. So this is how you'd find the distance so say you had this function in the xy plane and it models the position of a particle or position of a car or position of a person. And then if you can use the arc length formula, you can find the distance that the person traveled by integrating its position rather than working through its velocity. So these are pretty simple in the AP test. I'll show you what they look like. They show up from time to time. You honestly normally don't even have to evaluate them. It's just a setup kind of situation. So it's very important to know this equation. So arc length S stands for arc length. So S is the integral from a to b of the square root of 1 plus the derivative squared dx. Now we've got two different formulas here. One's in terms of x and one's in terms of y. Things to remember, if you're in terms of x, everything has to be in terms of x. So your function's in terms of x, your lower limit is an x value, and your upper limit is also an x value. Now when it's in terms of y, your derivative or your differential is in y, the function itself is in terms of y, and your limits must also be in terms of y. So everything has to match, otherwise it's not going to work. Okay, I already have these worked out just to save some time as I write them. But one thing we can do is we can verify the distance formula through this length. Now in middle school, when you verify the distance formula, what you did is you looked at it from a Pythagorean theorem standpoint. So distance formula of a straight line, well, it's just a right triangle. So the base of the right triangle is just x2 minus x1, and the height is y2 minus y1. And then the Pythagorean theorem says you do the base squared plus the height squared, and then you take the square root. So that's where the distance formula came from, but that only works when it's linear. So the problem is, in our world, things aren't always linear. So we need to be able to account for how can I add up these things. So essentially what you're doing, though, is little baby distance formulas on curves, and then you're just accumulate them over time with an integral. So I got my formula. So it's just the integral from x1 to x2. First thing is I need the derivative. Now derivative means slope. So the place I got this from, that's just your slope of the straight line. So change in y over change in x. All right, the next thing I did is all of this is a constant. So since all that's a constant, I can just take it out front of the integral. So this is a constant. None of that is a variable. The variable here is an x, which we don't have any, so you can imagine there's a little 1 there if that makes you happier. So then I take the antiderivative of 1, which is just x, okay? And then you're going to distribute x2 and then x1. So that's where I got this, x2 minus x1. That's from plugging in the antiderivative. All right, so now there's a little bit of algebra trick here. So what I've done is I've squared x2 minus x1, and I've taken the square root. So the net change there is none. The reason I did that is because now I can, since they're both portions of my product are under the radical, I can combine them under that radical. So the next thing I did is I distributed x2 minus x1 squared to both terms of this binomial. All right, so 1 times that product is just plain old x2 minus x1 quantity squared. And then when I multiply it here, what happens is the denominator can go away. And I'm left with y2 minus y1, which is what we know as the distance formula. All right, example 1 here is just a very simple check. So let's see that this is actually working. So it gave me an ordered pair, zeros, actually gave me a function 2x, and then from 0 to 4. So that's this position, this picture. So I'm trying to find the length of this arc. which I know is a straight line, which could be better done with the distance formula, or just thinking of it as a triangle, which is what I've done here. So the old way is the base squared plus the height squared. You wind up with the square root of 80 using Pythagorean theorem. Now the new way, which is totally not how I would do this problem, I would do it the old way, but just to see that it works, we got my integral. Remember, it's the derivative in here, so don't put a 2x and write it out every time. The square root of 1 plus the derivative squared dx. So the derivative of 2x is just 2. Square that, you get the square root of 5. That's just a constant, so I took it out front. Antiderivative of 1 would be an x. Plug in 4 and 0, you get 4 square roots of 5. These are the same things. You can simplify your radical. 80, factor of 16 times 5, square root of 16 is 4. So it seems to work. Seems like this thing works on straight lines. So let's see how it works on curves. Now, the good news for us is most of the questions on the AP exam about these things are in just setting them up. So you're really just picking them. But when you evaluate them, you kind of get this one. There's a few little tricks that show up almost every single time that we need to be well aware of. All right, so I set this thing up. So I got the square root of 1 plus, this is the derivative. So I went ahead and previously took the derivative and plugged it in. Now the next thing I did is I FOILed it. So I FOIL this out. I FOILed it out and I added the 1 in. Okay, so that gets me to here. Now, this is a step that shows up a ton. You're going to get some fraction almost every single time. And the fractions are hopefully made up of perfect squares in the denominator. And when they have those things, what we can do is we can factor out those fractions. So what I've done is I've factored out a 1/4, if you will. And I've taken the 1/4 out front, and then from there I took it out to the front of the integral itself. Now you got to remember to take the square root. So when you come out of the square root, you got to use the square root. So that's where this 1/2 comes from that we see. And then what's left in the square root is x to the 4th plus 2 plus x to the negative 4. Now that's really helpful because that is a perfect trinomial. So if you were to go complete the square, that's the kind of thing you would get. So the next thing I did is I rewrote that trinomial becomes this perfect squared binomial. And the great news about that is the square root of that square can go away. And that turns this into a much easier integral to finish by hand. So that's a weird process, especially the first time you see it. But I distributed everything out under the radical. I factored out a coefficient of 1/4, which became a 1/2 out front. Here's the kicker. This becomes a perfect trinomial. Those are hard to recognize, but the first term and the last term are perfect squares. And I can rewrite that as a perfect square binomial, which allows me to use the square root and get rid of it, which makes my integral way easier at that point. Don't mess this up. So many people do such great things, and then they're going to take the integral of x to the negative 2, and they either subtract 1 or don't add 1 right or something. But x to the negative 2, remember you add 1 and you divide by the new exponent. So your final answer here would be 33/16. All right, example 3. Now example 3, they've presented my function a little differently. So from the get-go, it's not solved for either variable. So that's a big hint. Honestly, you're doing this one in terms of y. It could be done in terms of x, but the integral can't be finished by hand in terms of x. So if you tried it in terms of x, you can set it up and you could get to a point where you could plug it in your calculator, but to finish it, evaluating it by hand wouldn't be something we could do. Now in terms of y, you can look at your multiple choice. This is normally almost always a multiple choice question. Look at the answer choices. If what you see are y's, dy, 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 that's your hint for doing it in terms of y. The thing to remember when you do something in terms of y, so the derivative is in terms of y, your variable is y, but the biggest thing is your limits are y values. Okay, so that's the one thing people screw up the most. These are x's. So 0 to 8 are x's. It's the x value. So what you need is the y value where this thing starts and where this thing stops. So that's where I got 1 to 5 from. So be very cognizant of your limits matching your variable. On your multiple choice AP questions, a lot of times just using the idea that I need to change my limits will get you the right answer. And you'll at least be able to get rid of several wrong answers by doing that. All right, so look through this problem. It's messy algebraically, so there's some picky stuff. I tried to show my work, see if you can get to the final answer. Now, this is far enough. There's really not much more. We could do a little bit more than that. You could simplify 4 to the 3/2, take the root, then cube it. You'd get an 8, but that's far enough. All right, last one of the notes today is example 4. So we got to do a little bit of trig. Otherwise, we don't want anyone to be sad about not getting their trig. So my function here is y equals the natural log of cosine of x. So the first thing I did is I went ahead and took the derivative. So here's my derivative. So remember the derivative of natural logs, the derivative of the input, which is negative sine, over the input itself, which is cosine. Simplify that to negative tangent. So my arc length is the integral from 0 to pi over 4 of the square root of 1 plus the derivative squared. So this is my derivative. Now pre-cal makes this a much easier problem. So if you square negative tangent, you get regular tangent squared. And then from here to here, I'm using my Pythagorean identity. 1 plus tangent squared equals secant squared. And then the square root of secant squared is just secant. Okay, and then the integral of secant is the one that you always laugh at me every time I write it down, but we've now written it down like 10 times in class. Integral of secant, it's probably one that you should know for sure, just like you know integral of sine, integral of cosine. So integral of secant is the natural log of secant x tangent x. Plug in pi over 4, you get down to your final answer. All right, that's it.